Today we want to share with you an engineering psychology perspective on action regulation in human-AI interaction. We will talk about the psychology of intelligent automation, and we will do this from the perspective of one exemplary context in the domain of health. But first, let's start with a very basic question. So what is technology? What is technology? Technology has various forms, but I would say that in general, technology is a tool to facilitate the regulation of valuable resources. That's also a key task then for all systems applying artificial intelligence, so supporting resource regulation. Because in the end, life is about the regulation of valuable resources. So we breathe in, we breathe out, we utilize our muscles to accomplish tasks, we select food to gain energy and invest in our health. So we invest time to gain information, to learn something new. So there are lots of resources. And if you think about it for yourself, so what would be valuable resources for you? Maybe time, maybe health, energy, money, friends, social life. So there's lots of valuable resources that we regulate. And I would even say that every second of our life is resource regulation. So the regulation of resources is an everyday task. One could even say it's every second. And interestingly, irrespective of whether it's time or money or energy, mobility or health, very similar or even same psychological principles apply to all kinds of resources. First, of course, we prefer winning over losing. But we are not completely rational in this. For example, our prospects shows us that losses hurt us twice as much as gains give us pleasure. So losses and hurts, of course, in the same amount. And there are further phenomena in bounded rationality and behavioral economics, like framing, anchoring, or if you think about intertemporal decision making, which is also particularly important in health context. There's temporal discounting, so we devalue gains that lie further in the future. There's a lot of effects, but that it might look like it's like discrete choice anomalies. But in everyday life, of course, resource regulation is not an activity of a single discrete decision or choice. It's a continuous process. So seen from a psychological point of view, resource regulation is action regulation, so goal-directed behavior, which is in the end a constant interaction of cognitive and motivational process. So on the one hand side, we set goal and pursue them, so it's motivation and volition. And on the other hand side, in this process, we have to perceive, evaluate, control environmental information and behavior, so cognitive processes. And we can think of this resource regulation as a continuous feedback control loop, so kind of a cybernetic perspective. And indeed, this is somehow a core component of many resource-oriented psychological models, like, for example, the transactional model of stress of Lazarus and Folkman. So to regulate our resources in a dynamic environment, we have to assess relevant environmental information. So there needs to be a certain perceptual or input function. And we must compare this with perceived state, with our goals. And the stronger or bigger the discrepancy between actual and target state, the more we try to compensate for this discrepancy. So let's focus on one specific example. Let's say we take glucose, so our blood sugar, as a resource. So normally, as we all know, glucose is regulated by our body without our intervention. So there's an autonomous homeostatic regulation of glucose and insulin. However, for example, people with diabetes mellitus do not produce insulin. So for decades, they relied on a manual process in which they needed to regulate according to this control loop. So first, measuring their glucose level in their blood, and also think about the last time and amount they injected insulin. Then this information needed to be compared with specific glucose goal values derived from therapy goals, which can be different in the morning or in the evening. And then the resulting discrepancy between the current level of glucose and the reference value needs to be used to decide about injecting insulin or eating to maintain the target glucose level. However, there can be disturbances in this process, for example, running fast to catch a bus or accidentally consuming a soft drink with sugar instead of a diet one. So my output function and these disturbances will together affect the glucose level and so create new dynamics in this control loop. So intelligent systems have the potential to support users in this resource regulation by automating parts of the information processing. And this can be seen in this graph here. So how do intelligent systems integrate with this control loop? So let us again stay inside this example and consider intelligent automation that helps people with diabetes to manage their glucose levels. So there are, in the end, 5 starting points where digital resource assistants can support action regulation. First, on the left-hand side, input support. So technology can relieve perception and information storage. For example, by measuring with digital sensors, which deliver information in a high frequency or also are able to save lots of information from the past. Second, goal support. So technology can, of course, also help us to estimate the correct and realistic goals. For example, by situation-specific adaptation of goals based on medical considerations. So, for example, to realize a smooth transition between different glucose levels. Third, comparator support. So technology can support us to make comparisons easier, so as easy as possible best. For example, by adding information on predicted trends on glucose levels, oftentimes supported by color coding. Fourth, output support. So technology can also support us in our behavioral output regulation, for example, by suggesting the amount of insulin to be given or by applying it even autonomously. And finally, anti-disturbance support technology can also help us to anticipate and compensate for disturbances, for example, by anticipating based on daytime or other context factors, the likelihood of critical low glucose events. So intelligent systems in the end need to be well integrated with human resource regulation. So in the end, for optimal effectiveness of any intelligent automation, human-centered design is crucial. And in engineering psychology, there are quite some relevant concepts to structure the design space for human automation interaction. So one possibility to start with is, of course, to look at the levels of automation, how this impacts human system interaction and resource regulation. And here, usually up to 10 levels are or can be distinguished from a system that level 2 offers complete set of decision action alternatives to up to a system that decides everything, acts autonomously, and ignores the human. So let's apply this to our example context. So a regular insulin pump software can be best described as level 2 automation. So it requires completely manual regulation of all variables by users. It only helps to structure the available decision and action alternatives. Then there are open loop systems that are more advanced because they can provide suggestions to users, so how much insulin would be appropriate. However, the insulin injection and therefore the final decision about the final amount is still users' responsibility. That means users still have to integrate further context information. So this can be seen as level 4 automation in this system. And finally, hybrid closed loop systems go even one step further because they automatically regulate insulin and inform users only if asked. So conceptually, there's a fine-grained space of possibilities, and this idea of levels of automation helps us to understand how autonomously humans and machines act in a shared task. And at least these hybrid closed loop systems are clearly an example of an artificial intelligent assistance system for resource regulation. Now, another possibility to structure this intensity of automation is to look into which stages of information processing are automated to which degree. So Parasuraman and Sheridan, for example, use a simple model of information processing that distinguishes 4 stages. So information acquisition, information analysis, decision selection, and action implementation. So these levels of automation are not just a one-dimensional space of possibilities. Systems can vary with respect to which information processing stage has which level of automation, yielding in the end kind of an automation profile. So while one system may offer a high level of automation in the phase of decision selection, another system may rather only automatically implement actions once the user has made a decision. So in the end, intelligent automation is about sharing tasks or part of tasks of information processing. And of course, how this is done has quite relevant psychological implications. So what is good automation is essentially dependent on how different task sharing modes impact the human, and 4 concepts are especially important here. First of all, of course, trust. So especially in vulnerable situations, as in our context, where users rely or have to rely on the end of, also on automation, their attitudes towards the competence of a system is very important. So how reliable and traceable is the system? Is it able to solve the task? So insufficient or too much trust can be highly problematic in this human automation interaction. So under trust on the one hand side can result in inefficient use of the system and may prevent users from reaching the level of performance that could be easily achieved with the system. And under trust and on the other hand side, over trust may reduce the level of monitoring users show, or leading in the end to fatal consequences. So in diabetes, for example, glucose sensors work precisely most of the time, but can fail, for example, after physical activity or in great heat because of sweat. So here users must adjust their level of trust in dependence of context in order to treat the calculated results correctly. Second, there's situation awareness. So automating the information processing may limit the user's awareness of changes in the environment and the system itself, since they do not need to process the information on their own, so they are somehow out of the loop. So there's the risk that users are too much out of the loop to develop a sufficient situation comprehension in a given situation. And this may lead to false decisions or when users still have some role to play in the system. So, for example, in highly automated diabetes systems, users may lose awareness regarding the currently active insulin in their body. So it's also what you call insulin on board. And for this reason, manually insulin pumps communicate the current insulin on board when a user wants to administer more insulin. Then there's mental workload. Of course, basically, we aim to reduce mental workload with automation. So in diabetes, of course, manual calculating the current insulin needed may generate a lot of mental workload and can be automized. On the other hand, a continuous need for supervision of such a system can also cause additional workload, other workload. And finally, skill degradation. So when intelligent automation takes over certain functions of the information processing, that may lead users to, in the end, losing skills, so not even being able to carry it out, the actions out for themselves. So, for example, in diabetes, the automatic calculation of insulin may reduce workload, but can also users to forget, for example, to apply different factors in the interpretation and calculation in the morning and the evening. So many of these challenges of automation then can be addressed if this cooperation and communication between users and system is well designed. And therefore, I think that this is a good point to proceed here. Yeah, and this is also the point where I hand over to Tim to talk about exactly this and start with the control loops that the system has.
Yeah, thank you, Thomas. Can you see my screen now?
Yeah.
Does it work?
Perfect.
Perfect. Okay, so thank you very much. Yeah, the question now is, how does this idea of intelligent automation in the context that we showed you before actually influence diabetes, and what role do explanations play finally when we want to improve the collaboration between humans and intelligent systems? So like Thomas said before, modern care for type 1 diabetes relies on something called hybrid closed loop systems. This is what you can see here. And it is hybrid because the automation here still relies on human input to achieve its high performance. Because now here we look at how the machine works. We look at the machine's control loop. And we see there's tissue glucose levels detected by a sensor. This is what you can see on the bottom. But we also need information from the human, which is exclusive to the human, about activity and nutrition. And only when those work together, the system can calculate insulin levels automatically and address it automatically or make suggestions. So the information for the system must be available in time to choose the correct amount, for example, of insulin in the output function. And this information, which is exclusive to the human, needs to be communicated so the cooperation between those two partners can work. And from our point of view, this example illustrates why we have this importance of psychological concepts that Thomas outlined just before. It is extremely necessary that the users can comprehend the system and allow them to see what impact a timely disclosure, for example, of their food intake or of the activity has on the algorithm or not. And at the same time, this may generate workload, but at the moment there is no full automation possible because we have no sensors for the activity and nutrition. So in especially this case, it's interesting to look what explanations may can do. Another example also illustrates the further need of transparency and explanations in this study. So, for example, if a diabetic person is driving alone at night, then critically low levels of glucose can be extremely dangerous. So maybe the desire arises that the automation completely prevents those events by, for example, setting the aim value higher. And in this act, the target value that the system has currently needs to be transparently communicated so the person is able to adjust it. And when we look at another variable that we discussed earlier, for example, trust, then we can also see another issue that rises here. So oftentimes, trust issues in automation and AI are discussed when systems may be faulty or at least capable of suboptimal performance. Don't want to go much into this detail now because, for example, in diabetes, there's another reason for lower trust: violated expectations. So diabetes, a person with diabetes, they don't check the glucose levels as regularly as a system may can, because they need to check it with the blood at the finger and have not a sensor and no frequent high frequency in the glucose measurements. So they work differently with the resulting data. For example, a system that has very fast access to the data maybe tries to lower the glucose level step by step to avoid critically low situations, while people may tend to give a larger amount of insulin at one time. And as a result, the system actions may not meet the expectations of the person who is using it, don't seem reasonable, and therefore a potential loss of trust can result. And this is closely related to a missing explanation or a lack of traceability of how and why the system works differently than maybe the user did it before. So we are here to speak about the effects of XAI on all those different factors that we described before. And we see theoretically that there are different points where explainability can benefit the interaction between users and the system. And this is why we want to speak about cooperation and what we need for two systems to cooperate, or for a human and an AI to cooperate. So when some parts of the information processing activity are shared between humans and machines, as Thomas described before, then it is necessary for both to communicate and share information about those results of the sub-processes. For example, if a machine would automatically detect the glucose level, but would not comment or communicate it to the user would be lost and could not go on with the information processing because there is an important information missing. So the way communication, the interface between those two partners is structured, can be very important and allow for cooperation or not, or to different degrees. So when we discuss explainability of intelligent automation, we also discuss which information a system is able to communicate to ensure cooperation, and when and how it will do this. And when we speak about cooperation, there's a definition from Klein et al. About joint human agent activity, which has 4 main points. The agreement of 2 partners to work together, a common ground, and the common ground directly refers also to the idea of situation awareness we introduced before. Here, partners need to communicate intentions, goals, or beliefs, for example, about the current glucose level or the current insulin level in the body or other relevant resources, so they stay predictable, which is the 3rd factor, mutual predictability of our actions, so that you can assume how will the system react if I proceed a certain action, what will be the reaction of my partner, and a mutual directability. And this is a very important point here, because directability means that easy but powerful signals allow for both partners to change their way to process information and act. So when I, for example, change the target value of the automated systems, this would allow the system to change, and I have the possibility to direct the system. A very important factor for cooperation, which we can enable by explanations. So what does that mean in our specific case? Let's go step by step through the machine's information processing again and see what is communicated in each step, because this is a chance to structure where which explanation can take place. So we look at the machine's information processing in terms of a control loop. In the first step in the input function, a machine may show which information has entered the system for this information processing or not. So users can agree, change, or adapt this information, for example, when they don't agree or when it is, for example, not legally fine that this information enters the information processing. Second, there needs to be a shared intent. So to create this and allow for directability, the machine informs about its goals it pursues. So users may change those goals when they understood them to direct the machine's behavior in their own interest. When we look to the output function, meta information such as weights may help to evaluate trustworthiness of the calculation, of the output that is generated in the process. And it allows users to request maybe additional information. For example, why is a specific value not weighted this way, or what would happen if I would weight this specific information higher? So that they can finally decide if they want to accept, maybe modify, or restart this process. So if they are satisfied with the result at the end of this cooperation. So what does that mean for our explanations in the diabetes example? How can explanations now look like? And this is maybe a very strange assumption when we look from a lot of the XAI literature, because it is very focused on this local domain of this resource regulation that is happening in our specific use case. So let us look again of the first transition point that we spoke about before, the input function. It is important that the system represents the information it gathered. So in case of diabetes, for example, the system could indicate that it has not received information about nutrition and assumes that no food has been ingested. So presenting this information is an accessible way, explaining the information processing of the system and helping the user to uncover discrepancies between their own beliefs and the beliefs of the system. That strengthens the common ground, which is necessary cooperation. In the next step, the loop system performs an adjustment based on the goals that is set within and the user preferences it has. So the question is, are there maybe other requirements important to the users which are not listed to avoid critically low events? This information can also be provided by communicating current valid target values and reasons for this target value. This is not only very important to ensure directability, but additionally helps to explain the process of information processing that happens within this system. So here too, knowledge about the state of the system is improved for the user. Namely, it becomes clear that the system wants to correct, for example, the level downwards or wants to raise the level and will stop the insulin delivery. So the intention of the system that results from the comparison between the input and the reference functions here is made clear. And in the last step, there's also the possibility to explain the output. And this is what many of the explanatory approaches currently discussed in XAI do. They allow, for example, for counterfactuals, or in other words, change certain parameters and see how this affects how the result is presented, and show weights, for example, or let people change weights, and helps to understand the concrete calculation that was performed within this information processing. So this also can increase the confidence in the system, unfortunately, also sometimes when it is not justified, but I will speak about this in a second. It can also help to make future results more predictable for the user, because the influence of certain aspects in the information processing can be better estimated. And the experienced predictability of a system ultimately is also central criterion for trust and also for cooperation, as we remember. So there are also already different empirical studies to all the factors we explained. I will speak about 2 studies shortly. One study is quite recently from Bansal et al., and they were able to show in the study that the additional information provided in a human AI team helped to increase performance of this team. However, the probability that a human accepts the proposal of the AI, regardless whether the AI's proposal was correct or not, was also higher. So explanations affect the trust here in this, based on the system's recommendations, not always in a desirable way. So what they did for this purpose was a text classification task, is one of different tasks for users, setting up the evaluation of peer reviews and deciding if those peer reviews were mostly positive or mostly negative, supported by an AI. And you see here the screen that they used in their study, and I would like to highlight 3 different aspects of the user interface: the robot face that indicated the AI's recommendation, the graph beneath that depicted the confidence level of the AI, and an explanatory text interface, which were present only in explanation conditions, where certain words were highlighted, trying to show why the system thinks a review is positive or negative. And they expected to find a positive of explanations, what we would maybe do at this position in the talk as well. However, it's not that easy. Here you can see the shared, the accuracy of the shared teams. Like if the human is alone, the accuracy was clearly lower, but then all the other different conditions, and the first condition under human that you can see is only showing confidence, but no further explanations, did not differ significantly from each other. So compared to just showing the AI's confidence or adding an explanation, there were no difference found. But worryingly, and this is the second image that I want to show you, if you look at the green dots, they show when the AI made a correct suggestion, how's the shared accuracy, and the red dots show how the shared accuracy is if the AI made wrong suggestion. So we see here that there's a clear difference between confidence and the first of the explanation alternatives, which is also significantly. So this study is of course not the first one, but one from a few now that show that there can also be an inappropriate trust resulting from explanations. And how can that be? What can we do? What can we learn here from automation psychology? This is also one of the points that the authors draw from here. We need to design explanations to be informative rather than convincing, because when they are convincing rather than informative, they can lead to overtrust and then therefore worse performance. And this is one point where I would like to refer back to our regulatory loop to try to decide which explanations are informative in this moment for the user or not. There's another study that I wanted to show you. It's done by Kim et al. And they compared also different recommender systems for movies. And among other things, they addressed the question of detailed feedback, or the possibility to give more or less detailed feedback. So one group here could only assign a like or a dislike button, and the other group had a chance for a more directable approach with more detailed feedback options. So, and here we also find the more detailed condition quickly led to a higher acceptance and to better comprehensibility. And the problem that directly jumped into my mind when I read this was, okay, but what about a workload here? And this study also tried to understand the subjective perceived workload with the NASA TLX, and this was also lower for the more detailed condition. And I think this raises the questions whether the directability that we apply in a system, communicating goals and also allow people to change and direct these goals and weights differently, can have an influence on the perceived workload, on the perceived comprehensibility, and the perceived trust, as shown here. So at least for this study, we can state that explanations on how a system predicts the results do not necessarily overwhelm participants, but instead can also provide them to gain confidence more effectively when they are able to provide detailed feedback in recommender systems like this one. So the opportunity to give detailed feedback reduces the mental demand, effort, and frustration significantly. What many of the current research also states, or what you can find here and there, is that the claim that the mental model of users can be changed by explanations, which is a very interesting topic, because oftentimes this refers to the qualitative data, which is measured within the study, because the quantitative analysis of mental models still proves challenging from our point of view. So we need to discuss the empirical evidence for explanations, their effect on situation awareness, one of the constructs that Thomas also mentioned before. And this is what we are interested in our research, which quantitative measures for such systems are available and applicable. And I brought a few of them here. We'll go through them fast. So there's one, for example, the situation awareness rating technique, also called SART. However, the SART is an instrument that is quite broad and addresses from psychological perspective different levels, like there's mental workload included directly in this construct instead of separating it from the situation awareness as a construct. And in general, maybe it is a question if it's better for changing environments than for a specific human-machine interaction. There is the system causability scale from Holzinger et al., which is based on the system usability scale. So it provides a quick superficial overview of a system and how the explanations are rated. But the thing here is also that while it is a very good starting point, that there are direct mentioning of explanations in the items, which is especially when you want to make, for example, an A/B testing or compare explanations as a independent variable challenging. The same problem is with the explanation satisfaction scale from Hoffman and al., which also directly addresses explanations. However, it always exactly refers to explanations as a construct and let people rate explanations. So has maybe a more selective measure here, but it is also aimed for more experienced users, which are another barrier depending on which kind of research you want to do. So we said there are different requirements to develop an instrument that we can use here. One that can be used after a single interaction, does not need a long time or repeated interactions, that it can be used without explicit explanations to allow for comparisons, aimed at the subjective interaction experience of people and focuses on this based on this different levels of situation awareness, which are the percepting, the understanding and the projection of the situation I am in. So we have combined these factors reflected in the different levels of the aforementioned situation awareness and their experienced counterparts as system properties, transparency, understandability, and predictability, which we refer back to the different points of explanations I mentioned before, and transformed this into a scale that we already used in a medical context. So we moved from situation awareness to subjective information processing awareness, developed the 6-item scale with 2 of the 6 items, each corresponding to one of those system properties. After many iterations and expert feedback, and tested it then in a study with a medical AI. And this is the scenario that I wanted to show you. So we looked at a system that can assist in the diagnosis of deep vein thrombosis, which is done via ultrasound images, and tries to find out if the vein in the leg is closed or not. And the final decision is always made by the medical professional, but we really wanted to understand if we also show the screen to a potential patient, how would they react? How would this affect their trust, situation awareness, and so on? And as you can see, we have two different independent variables that we wanted to test out here. One is the level of detail of information that we give, so trying to change the information about the input function that the system has. So on top, you can see this was a within condition showing detailed information, or down showing on the down showing the detailed information, or on the top just showing the information category. And between two groups, we also showed a label that states that all data was successful obtained or not. And here we measured trust, explanation, satisfaction, and the SIPA scale, so the subjective information processing awareness. And we actually found an effect here with a D of 0.42 for the condition where we showed a rather detailed or undetailed depiction of the information, but for the between condition, we did not find a significant difference here. So how does this relate to trust, for example? And I think this is very interesting because we found significant significant correlations in both conditions. However, they are maybe not as strong as we expected before. So maybe the idea that the understanding of the system and trusting the system are and need to be treated as separated constructs for the evaluation of explainable systems. However, when we looked at explanation satisfaction, we found that there's quite a high correlation, which is also strongly significant, which speaks for convergent validity for the construct here. So very interesting also for A/B testing. So what can we do now as researchers? Because there's one point that is still missing and very important, because we discussed a lot how does people subjectively experience this human automation interaction and the information that they are getting from the system about its information processing. But it's still unanswered question is, how does this affect also the performance between humans and machines? So in our current experiment, we're investigating the effects of the amount of information this is presented. So an intelligent system here is calculating insulin requirements based on different information types. And we either show just one or different columns of information and try to find out how does this in repeated interactions, how does this result in workload, in trust, in subjective information processing awareness. And then finally also people have to predict the work of the AI, the calculation of the AI, to see how does this affect the performance that people have in predicting AI systems. So when we look at the engineering psychology and what is the most urgent agenda point in XAI for engineering psychology, it is to develop informative, low workload explanations which support the calibration of trust and perceived understandability without leading to overconfidence. And in this regard, the research on information processing in combination with the representation as a regulation loop, this can provide starting points for explanations that support just that. So explanations remain oriented to the human process of action regulation and serve to assist in one of the three processes that we discussed today. So the explanation of input information, the explanation of reference values used by the system, or the explanation of calculations and results done by the system. Certainly, every use case here is different, and the diagnostic process maybe is more complicated to be treated like a continuous loop than today's diabetes example. But the main takeaway is simple, I think. The insights from engineering psychology in automation can be the basis for the next steps towards a human-centered, explainable artificial intelligence. And with this, I would thank you for listening to us and our ideas about automation and action regulation. Hope you have some questions for us to discuss.